looking at is how to use the dye dilution method in order to determine the volume of different body fluid compartments. So we know from class that normally we can use inulin to measure the extracellular fluid volume by the dilution principle. But in this problem, we have a case where some of the inulin unexpectedly begin to bind to albumin. So in order to solve this problem, we're really going to have to think about the different body fluid compartments, how we use the dye dilution method, and how different changes in components of that equation might change our ability to determine the volume of different body fluid compartments. And we'll also have to think about the concept of reflection coefficients for different compounds as they're traveling through the body fluid compartments. So what I always suggest is the first thing that you should do whenever you're solving a problem like this that's using the body fluid dilution principle is I would go through and write up the equation itself. It's going to be much easier to think about how it might change in this situation if you actually have the equation in front of you. So the equation that we're looking at is, in order to determine the volume of a body fluid compartment in milliliters, we would look at the amount of a particular dye that we're using, which is measured in milligrams, and divide that by the final concentration of the dye. And that final concentration is going to be in milligrams per milliliter. Now, one really important concept when we're looking at this dye dilution method is everything that we're putting into the system, everything that we're taking out of the system is through the plasma. So when we're talking about the amount of the dye that we're adding, we're talking about the amount that we're actually adding into the plasma. When we're talking about the final concentration of that dye, what we're talking about is what is the final concentration of the dye that we would detect if we took a sample from the plasma. So those are two values that we would measure. We're going to use that to actually calculate, well, what is the volume of a specific body fluid compartment? So we have to know what the dye is that we're using, where we would normally expect that dye to go. So I think it helps to have a visual representation of where inulin would be going normally, and then we can talk about, well, what would be the situation here? So if we think about our major body fluid compartments, we would have the intracellular body fluid compartment. And what we would see is that would be surrounded by the plasma membrane. Then we're going to have the interstitial fluid body fluid compartment, that fluid that's going to be bathing all the cells of our body. And then last but not least, we'll also have our plasma. Now, the reason why I've represented that boundary between the plasma and the interstitial fluid is dashes or dots in this case, is because those are endothelial cells. And we know that endothelial cells have clefts between them that will allow many of our smaller molecular weight molecules to actually pass through those clefts. Now, we just mentioned that everything that we're actually adding into and taking out during the dye dilution principle is through the plasma. So if we were to add our inulin, we would be adding it into the plasma. So we're just going to draw it up as some circles. Now, you should know the different components of inulin, what its characteristics are. It is going to be a large molecular weight carbohydrate. We also know that it has a small enough molecular weight that it is able to go through those endothelial cell clefts, and it would also be able to equilibrate in the interstitial fluid as well. So for that reason, we use inulin as a marker to determine the volume of the extracellular fluid because it equilibrates in all of the extracellular fluids of the body. So if we think about our normal values, typically we should see a plasma volume of about 3 liters, an interstitial fluid volume of about 11 liters. So overall we should see through our measurements with the dye dilution principle with inulin should be equilibrating in a volume of about 14 liters. Okay? But we also know in this problem there's something abnormal going on with the inulin where it's not going to serve as a very good indicator of the extracellular fluid volume. So let's draw up right below this the situation that we would be seeing whenever we have some of our inulin that's actually binding to albumin. Okay. So once again, we have the same body fluid compartments. We would be adding in our inulin and it would be going into the plasma. But we have an interesting situation here. It's mentioned in the stem of the problem that instead of inulin being able to freely pass out through those endothelial cell clefts, go into the interstitial fluid, here what we're seeing is inulin is actually binding to a large protein, which is inside the plasma called albumin. So albumin is a very large molecular weight protein. It's actually too large to come out through those endothelial cell clefts. So here we have a situation where the inulin, because it's binding to that albumin, isn't able to freely pass out into the interstitial fluid. Now remember that when we're looking at our final concentration up here, the way that we're doing that is we're determining it from the plasma. So we're looking at what is that final concentration of inulin that we're taking out of the plasma. So what we would see is there is actually a higher inulin concentration in the plasma than normal. So we have to go back up and look at our equation. That's why we had to write it down. We have to think about, well, what would be changing in this situation for our dilution principle? So we just said there's an increase in the inulin concentration just in the plasma. Remember, that's where we measure it from. So what we would see is the denominator of this equation is going to be going up. Okay? Now, the numerator, which was the amount that we added in the first place, that's going to stay the same. We still added the same amount originally, so that hasn't changed. But what we have done is increased the denominator of our equation. So if we're dividing by essentially a larger number, what we would see is the result of that is our calculated volume would actually go down. When you divide by a bigger number, you end up with a smaller result. And so based on the concept that we have here, where inulin's binding to that albumin, it would actually result in an underestimation of our true volume of the extracellular body fluid compartment. So because we've gone through this equation, we know that we should be looking for an underestimation. Okay. So just initially looking at that, we're actually able to eliminate two of our responses because two of them have an overestimation. But what I'd like to do is actually go through each of the different answers to this problem and talk about why each one was correct or incorrect. Okay. So if we go over to response A, it initially says underestimation, so we haven't turned anything off right there. It says that it's an underestimation because, remember because is always an important word here, inulin is excreted by the kidneys. Now, if inulin is excreted by the kidneys, what we would see in this case is our final concentration that we would measure in our plasma would actually be lower than normal because that inulin that we would expect to still be in the plasma is actually left, gone out through the kidneys. So in that case, if our final concentration was lower than normal, we'd end up with an overestimation, and that's really not at all what we're seeing in this case. So based on that reasoning, our because statement, we can eliminate response A. Okay. Now response B we could also eliminate because we already said we're going to be expecting an underestimation. So we know that can't be true. The explanation that they give is because plasma has a high albumin concentration. And that's actually a true statement. So if we had changed this question and said it's an underestimation because plasma has a high albumin concentration, that would have actually been a true statement. So we can correct that one to be correct, if that makes sense. All right, now for response C, that says underestimation, so that part's right, because inulin binding to albumin decreases the reflection coefficient for albumin across the vascular wall. Okay, so in order to understand whether that one would be correct or not, we have to think about our reflection coefficient. And the reflection coefficient is a number that ranges from 0 to 1. So what 0 means is free solute permeability, meaning that our solute can go right across the barrier that we're describing. What 1 means is an impermeable solute, meaning that the solute in question cannot cross the barrier. So if we go back over down here to the right-hand side and we were looking at our albumin, which was down here in blue, what we saw is it was an impermeable solute. It's not able to cross those endothelial cells' clefts very easily. So what we're seeing is albumin already sits right at 1. So in response C, it's saying that we have an underestimation because inulin binding to albumin decreases the reflection coefficient for albumin across the vascular wall. So what we're saying is essentially by inulin binding to the albumin, we're making it easier for the albumin to go through the endothelial cell clefts. And that just doesn't make much sense. If you have compounds that are binding to the albumin, it should, if anything, make it more difficult for that molecule with its associated solutes to move across the endothelial cell wall. So that response in of itself doesn't really make sense. What we should see is, if anything, there might be a slight increase in the reflection coefficient, but because we're already sitting at 1, you really shouldn't see much of a change. So our underestimation part was right. The reasoning behind this isn't very good, though, because albumin already has the highest reflection coefficient that it can, and that's certainly not going to cause it to result in our underestimation. So we can also eliminate C. All right, and the last one, D, we can actually eliminate as well because we already know we're looking at an underestimation. We determined that. And the reasoning is, it says because interstitial fluid has a low albumin concentration. It's actually a true statement. Interstitial fluid does have a very low albumin concentration. So if we had put underestimation, that could actually be a correct statement. But because we still have over, we also eliminate it. So what we see here is, after going through all the responses, the correct answer is actually E, none of the above. Okay, so hopefully this helped to clarify question number 10 for you. If you do have any further questions about this particular problem, as always, feel free to contact me.